here. All right, so the combined gas law is actually the one gas law that you should be aware of. But before we go over that, we're going to go over a third gas law very quickly. So recall last time we went over Boyle's law, pressure volume one, that P1V1 equals P2V2, and Charles' law, volume temperature one, V1 over T1 equals V2 over T2. Gay-Lussac's law is just relating pressure and temperature, that they're directly related. So in other words, if you increase the temperature of a gas in a fixed volume, its pressure will increase. Equation-wise, it's P1 over T1 equals P2 over T2. And then the last reminder on this slide is the temperature has to be in Kelvin. Now, we're not going to do practice problems with this one either, because usually we're not going to see questions that are just pressure temperature related. I mean, there could be a chance for that, but there's actually one equation that's a little bit more important for you to be aware of, and that's going to be called the combined gas law. That's what our next slide is. So actually, we're already a third of the way through the slides I have on this. So here we go, combined gas law. Combined gas law is when pressure, volume, and temperature are all possible variables. I would say this is the gas law you need to know. Remember, Boyle's law, the pressure volume one, is if temperature remains constant. Charles' law, the volume temperature one, is when pressure remains constant. Gay-Lussac's that you just saw was when volume remains constant. However, all these variables could actually be altered in any given reaction. Really, the only thing that would still remain constant is the number of molecules, so it is a sealed container. So it's called combined gas law because it combines Boyle's and Charles and Gay-Lussac's law. The equation, I'm actually going to switch over to the Smart Notebook to show you because it's just easier than writing. Even you saw on the last slide when you try to do an underline with a subscript, then it makes the underlined subscript as well as just goofy. So I'll give you a chance to jot this down, and then we'll switch over to write out the equation, which is a little bit easier than typing it out. So what I would say is you don't really need to know any other gas law except for this one so far. P1 V1 over T1 equals P2 V2 over T2. This is the combined gas law. Now the reason why I say you don't really need to know any other gas law except for this one right now is because if there's a question that says, let's say temperature remains constant, you could just ignore the temperature parts. And if you ignore the temperature parts, it's back to P1 V1 equals P2 V2. Well, we know that equation. That's just our normal equation dealing with Boyle's law. If it says that pressure remains constant, so ignore the P1 and the P2. And it's V1 over T1 equals V2 over T2, so it's Charles' law. So by knowing this one gas law, you've known all the gas laws that we go over now. Because if something remains constant, you could just give it the value of 1 on both sides, and then it just cancels each other out anyway. Again, this one, the only tricky part about it is keeping track of all the numbers. If you recall, with both the gas laws we went over last time, you were given 3 of the 4 variables. You solved for the 4th. Well, now you could be given 5 of the 6 variables. You have to solve for the 6th. The only issues I see with this mathematically is students sometimes mix up what was what. If I go back to my last slide then, a sample problem could give you something like this. What would the volume of a gas be at standard temperature and pressure? Remember STP, a term that we went over last time. That was 14 liters at 30 degrees Celsius and 0.50 atmospheres. This is actually a very common question, and next week, Friday, you have a lab, And in that lab, you will have to standardize your results. So remember last time I talked about the fact that every lab condition throughout the world is not identical, so that we have to standardize our results. Here is a suggestion I would give as you're doing this type of problem. Again, you don't have to do this entire problem right now. My suggestion would be is either as the question's written or off to the side afterwards, figure out what's my initial pressure. Okay, it was this. Initial volume, this. Initial temperature, don't forget to add the 273 because it has to be in Kelvin. Also notice that I have a decimal after the 30, meaning that one's place is significant, which is why I call this 303 and not just 300. Although then the tens place would be significant, Nick, and then we'd have to say something like 3.1 times 10 to the second, like you got, unfortunately, on website. P2, what will it be? Standard pressure, 1 atmosphere. You could call it 760 millimeters of mercury as well, but since this is already in atmospheres, sorry that I dropped the unit here, why not keep that in atmospheres as well? Asking for V2, T2 again, standard temperature is 273. So you want to organize these types of problems as you go about. To me, that's the key component of this. Now, some students will say, what if I mix up my 1s and my 2s? Doesn't matter. 1 doesn't have to necessarily mean the initial. If you wanted to call your P1 1 atmosphere and your T1 273 and you're solving for V1, that's okay. Just don't mix up the beginning and the end. However you want to label 1 versus 2, that's fine by me. But that's kind of the key of going forward. Last thing to mention about this then is if I were solving for V2, you have 2 ways you could solve for it. You could just plug in the numbers immediately then and solve for it. So that means you'd have to probably multiply by 273, which would be on this side here. You'd have to divide by the P2, which was 1, so I guess that's no work involved there. If you look at my answer keys, again, when I've been teaching this for a long time ago, especially the math department tried to emphasize isolating the variable before you plug in values. So if I were to solve for V2, it would be P1 V1 T2 over T1 P2. So sometimes if you look at my work, I then plug it in and solve. However you're more comfortable with it algebraically, go ahead and do it. I would caution you that the one time that students plug in first and then solve and it gets a little difficult is if temperature is the variable they're solving for. The more algebraic mistakes I see is when the variable is in the denominator, because it's not as easy for students to get rid of that when there's numbers up here, down here, and up here all at the same time. It kind of throws them off at times. So whichever method is best for you is what I would suggest that you do.